Hello, I'm Xin, machine learning engineer from Eliza. Today I'm going to talk about building serverless machine learning workflows. Workflow, I'm sure you're all familiar with what a workflow is, and here's an example. If you attend this conference, you might come to my talk. If you do, then you will have a good time, but if you don't, well, you are forgiven. If we expand this workflow a little bit more in a machine learning context, then we will have a machine learning workflow, and it generally looks like this. So we have a data import block or components to import the data, and then a feature engineering components to extract features from the input data. Then we train the model on the extracted features, and then we validate the trained model, see whether it meets the success criteria. If it doesn't, then we may have to retrigger the whole training pipeline again to improve the model training. If it does, then we deploy the model into a production environment as a model inference component. And on top of that, we would like to have a model monitoring component to monitor the model in production to make sure that it actually behaves as expected. If it does behave as expected over time, then it's fine. But if it doesn't, then we may have to retrigger the model training pipeline again to improve the model performance or accuracy. So this is the machine learning workflow in a high level. And today, I'm going to step into a machine learning engineer's story in reality to see how they implement such a workflow in the real world. In reality, machine learning engineer usually works with a data scientist to deploy models into production, and usually it implements the workflow mentioned above like this. So the story goes like the data scientist works kind of in silo to develop a model. And once the model is developed, they pass that model to a machine learning engineer. And the engineer would wrap the model file as well as the code to run it into a reproducible framework. And then they deploy that framework into production environment, which usually is a cloud environment. And this process seems to be pretty straightforward, but if we zoom in a little bit, it looks more like a protocol handshake process. And it goes like this. The data scientist does the model training, the model has been trained, and then the engineer acknowledges the model readiness for deployment. Later on, the data scientists realize there's some improvements can be done to the model. So a few days later, they improve the model and let the engineer know that the model is ready for deployment. And this time, the engineer might find some minor bugs in the updated model. So they notify the data scientist to do bug fixing. A day later, the bug has been fixed. The model is passed back to the engineer. Sometimes engineer might find some incompatible inference code with the updated model. So they ask the data scientist to update the inference code to work with the updated model. A couple days later, the inference code is updated, and this time the model is ready for deployment. So, and you can see this process is fairly manual and interactive between the data scientists and machine learning engineers. So the whole operation is manual and going back and forth between the two parties. And what are the problems from this process? On the general operation side of things, this process is manual and interactive, and there is disconnection between development and production. Data scientists works in a separate environment for model development, while the engineers deploy the model into a different environment for production. And there's no continuous integration or continuous delivery pipeline in this process. The development cycle is fairly long because of the manual process going back and forth between the two parties, and the process is not scalable. Also, it's prone to errors and bugs. On the machine learning side, because of the disconnection between development and production, there's potential risk of model training and serving skill or inconsistency. And the long development cycle usually leads to infrequent model releases, and there's no active model monitoring in place either. So how could we address these problems? We could potentially turn this manual process into a machine learning workflow, which can be automated in an organizational environment or infrastructure. In many cases, this infrastructure environment usually is in the cloud, and dependent on the use cases, implementing such a machine learning workflow within a serverless architecture has also been widely adopted. So the goal is to turn this Handshake manual process into an automated machine learning workflow in the cloud environment, which can be shared between the two parties, and potentially implementing such a workflow within a serverless architecture. Now, why serverless? For general operations, serverless architecture provides elastic compute resources, which is important for machine learning projects because different machine learning component or different machine learning project requires different resources as well as runtime. And serverless architecture also provide a more modular system, different services for various purposes, which makes the machine learning workflow definition more clear and the components more self-contained so that the work can be distributed in parallel among the team. So the data scientists can focus on the components relevant to model development, while the engineers can focus on the components more close to the model deployment. Serverless architecture also provides built-in auto-scaling, which is essential to machine learning practice, because prediction servers in machine learning applications needs to scale depending on the request load, and also the quantity of the models needs to be scaled as well. Whether it's within one project, there will be multiple models along the way, or multiple models across multiple projects. And serverless architecture in the cloud environment also obviates the configurations and management of long-term compute unit, which makes the engineers can focus more on the machine learning core engineering rather than having to deal with the infrastructure engineering overhead. For machine learning specifics, serverless architecture provides a more modular system that provides a more consistent infrastructure, which combines the data science workflow as well as the machine learning engineers workflow together into one unified platform to unify the machine learning operations. And it also provides flexible selection of heterogeneous resources for different applications or different stages within one application. For example, a computer vision project might require some heavy compute optimized resources such as GPUs, while a random forest classification application might not need that compute optimized resources. And within one application, the training stage might require compute heavy or powerful compute instances to speed up the process, while those instances might be overkill for inference stage. Now we know what we want to build is an automated serverless machine learning workflow. The next question is how to build such a workflow. And today I'm going to walk through an example architecture of such a workflow from my experience for a random forest classification application. And here are the components for the workflow. I use step functions as a workflow orchestrator to train all the components in a workflow together, and SageMaker to deal with the machine learning operations. I use the Lambda functions as the processing unit to handle the data processing or feature engineering those components, and S3 as data storage, and CloudWatch as an event scheduler for components such as monitoring schedule. And here is the architecture diagram of the machine learning workflows. So AWS step functions as the orchestrator. Then I have a Lambda function for data loading to load the historic data in batch for training. And then a feature engineering step to extract the features from the raw data input and put those features back to an S3 bucket. Then I have a monitoring baseline Lambda function to run a baseline and extract the statistic distribution of each feature in the training data set to set a benchmark for the data input of the trained model. And the result of the baseline will be put back to the S3 bucket. And then model training to train a model on the extracted feature from the previous step. Model saving step to actually save the model back into S3 bucket, as well as to deploy it as the SageMaker model instance. Then I have a training status query to retrieve the evaluation results from the model training step. The evaluation results can be defined before the model training, and so essentially it's just like a success criteria for the trained model, such as the accuracy score or the area under the ROC curve. And then I have a model validation step as a choice step to validate a model, to see whether the model meets the success criteria. If it doesn't, then I flag the model as invalid and exit the workflow. But if it does, then the model will be deployed as a SageMaker endpoint for future prediction and as an inference API. And that's not the last step, because we want to continuously monitor the behavior or the performance of the models in production. So we set up a monitoring schedule to do so. First, we need to enable the endpoint or the data capture on endpoints to store all the incoming data to a S3 bucket. And then we set up a monitoring schedule, essentially it's a cron job, to compare the input data with the baseline from the training data sets that is extracted from the monitoring baseline Lambda. And then we generate a monitoring report and put it back into the S3 bucket. Then we have like customized monitoring Lambda to actually grab the report and see whether there's any constraint violated. By constraint violation, I mean whether the incoming data still sits in the distribution of the training data. If it does, then everything is okay. But if it doesn't, then there's issue of model drifting or like the data drift, which means that the nature of the data has changed and the model has drifted, or the model doesn't perform as well as what we expect. In this case, a model retraining may have to be triggered. So the customized monitoring Lambda can potentially trigger the whole training pipeline to train the model again to improve the accuracy. And this is the overall architecture of the workflow. And I implement such an architecture using the AWS Step Function Data Science SDK. And here's what the code looks like. First, we need to define the pipeline of the workflow. Essentially, you would define all the different steps first. So we have data loading step, feature engineering step, baseline, training, model steps, and then training status step, as well as model validation steps. When a decision needs to be made before the workflow can be continued, a choice step can be used. And inside the choice step, you could use the rule to define the decision logic and also the next step accordingly. For example, here, the model validation step is a choice step, and I use the pass rule to indicate that the model is valid. And then we could proceed to the next step, which is the endpoint config step to deploy the model into production or as an endpoint. And I also use a fail rule to indicate that the model is not valid. Then the next step would be the fail step to indicate that, and then exit the workflow. The SDK also provides a next function to chain two steps together. For example, the next step of the endpoint step is the monitoring step in this workflow. Once we define the pipeline and the steps of the workflow, the next thing would be to define the input of the workflow. That is the input schema. You could define the input of the execution of the workflow like this. So you have all the input fields and then the type of those fields. So you can see here I have all the Lambda function names for the Lambda steps, execution role to execute this whole workflow, the input fields for data loading steps, the input fields for feature engineering steps, and the input fields for monitoring, model training, and model inference steps. Now let's have a look at each step. So first is a Lambda step. I use feature engineering step as an example. So you define the step name and then the parameters. Inside the parameters, you have the function names to indicate which Lambda function to run for this Lambda step. And then the payload essentially is the input or the event to that particular Lambda function. And you can see this path here is essentially is the JSON path of the execution input. And also you could store the result of this step back here as the input for the later steps in the workflow. The next is the training step. In the training step, you define an estimator or a training estimator. Essentially, it is where the model architecture or which model to use to do the training. And then you have the data, which points the steps to the training data location. As you can see here, I split the data into a train dataset and a validation dataset, and they are both in the S3 bucket. And then you have the job name for the training job, and a flag to indicate whether we should wait for the job to finish before continuing to the next step in the workflow. And worth mentioning that inside the training estimator, you could define some configuration for the training job. For example, the number of instances to use for the training and the type of the instance to use for the training. As you can see, I select the compute optimized training instance for the training job. Then we have model step, where the model has been trained and it's retrieved from the training step. And then in the model step, we will deploy the model as the SageMaker model instance. And then we have a choice rule to define the decision logic of a choice step. And the example of the pass rule here is that the training metrics from the training job, such as the model accuracy score or the area under the ROC curve, is greater than the predefined evaluation threshold. So this is the definition of the pass rule. To deploy the model into production, we need the final two steps, which are the endpoint config step as well as the endpoint step itself. So the endpoint config step, pretty self-explanatory, is that to define a configuration for the endpoint, which includes enabling the data capture so that the endpoint would store the incoming data into a specific S3 bucket, and also the endpoint configuration, such as the number of instances to run the endpoint or the type of instance for the model inference. And then the endpoint step to actually deploy the model as a SageMaker endpoint for future prediction. Now we have all the pipelines and the steps defined for the workflow, and we can have a look at what it actually looks like when we run the workflow. When a workflow is triggered, a state machine is created behind the scene in AWS step functions. And here's a definition of the workflow state machine. So we have the starting point and then data loading step, feature engineering, monitoring baseline, model training, save the model, query the training result to get the evaluation result, which is the success metrics, and I use area under the ROC curve as the measure. And then the success path includes model endpoint config, model endpoint, and the monitoring schedule. While the fail path just indicates that the model accuracy is too low, and then the workflow will be exited. And this is the actual execution process of the workflow. The blue blocks indicate that the component is in progress, while the green blocks means that the components have been executed successfully. In many cases, things never run as smoothly as you would have hoped, and you would almost always get some red blocks or errors while running the workflow before you would get like a nice green pipeline. So like this one. And it's extremely frustrating if the workflow failed in the last step, like here. So it would be great if I could just resume the workflow from the last failure point instead of running the whole workflow again. To fix the last step, especially some of the components such as the monitoring baseline and model training can take a little while to run or to finish. I don't think step functions has the built-in features to resume the workflow, but a workaround has been suggested. And it's suggested that you could use a choice step, such as a go-to state, to resume the workflow. So here's how it works. You have to pass the history of the failed state machine and get a name and input of the last failed step. And then you create a new state machine with all the steps from the original workflow, plus the choice step or the go-to state. Then if you want to resume the workflow, you could point the go-to state directly to the last failed step. In my case, it's the monitoring schedule. And if you don't want to resume the workflow, then you could just point the go-to state to the original starting point of the workflow, which is data loading, to run the whole pipeline again. And here's what it looks like to resume the workflow. So go to state, and I decided to resume the workflow from the last failed step. So it goes directly to the monitoring schedule and executes that component only to finish the whole workflow. So now we have the serverless machine learning workflow set up. And let's have a look at how the machine learning engineer's story ends. Once the engineer has set up the machine learning workflow framework, and they could hand that to the data scientist as a present. So with that workflow, the data scientists can finish their model development or model exploration and then commit the code changes. And once they commit some code changes, a CI/CD pipeline will trigger and to run the whole machine learning workflow in the cloud, like this. So this way, the data processing and the model training has been automated and continuously integrated, and the continuous delivery of the models has been achieved, and also active model monitoring is in place. So the data scientist is empowered, and the machine learning engineers can enjoy their precious cup of coffee. So with this automated serverless machine learning workflow, on the general operation side, the process has been automated, and we have continuous integration of both the development and deployment process. We have continuous delivery of both the model itself and the workflow, and also the continuous training of various models. And the development cycle has been sped up because of the automated process. The component modularity has been improved with the serverless architecture, and the whole machine learning operations is scalable, reliable, and reproducible. For machine learning specifics, we achieved experimental and operational symmetry because the pipeline used in development stage is the same as in production stage. So essentially, the operation has been unified. And with this unified platform and a continuous delivery of both workflow and models, the model training and serving is consistent under this platform. And the rapid development cycle and the continuous delivery of models leads to frequent releases of models, and active model monitoring is in place. So this is the happy ending of a machine learning engineer's story. Thank you.